Hello, everybody. Welcome to our new Algebra 2 Module 3, Topic 1. We are skipping Lesson 1, which is fine by us. It actually is kind of crazy. You have your little book in front of you, your spiral-bound book. You can look through it if you would like to. We aren't going to take time to cover it. It's optional. We don't have enough time in our schedule to keep going with it. So if you want to take a look at it yourself, feel free. I put the answer key from the workbook up on Google Classroom. So if you really wanted to go look at it, you are more than welcome to. So we are going to start with radical functions. So we're going to be talking about square root functions, cube root functions, radical functions, and composition of functions. Basically, we've been dealing with functions all year. We've covered exponential, we've covered linear a little bit, and quadratic. So linear was a line, exponential was that soft sloping curve, and a quadratic is a parabola. So as a warm-up, we have these three. So it says solve each equation for x. So number 1, you should be able to do, number 2, and number 3, honestly. So pause the video, practice right now in your own workbook, press play when you're ready to see them worked through as the answers. And I don't really want to talk while I do this, but I don't know. Hope your day is going well, guys, you know? Yeah, so if you're listening to me, cool. A little tickle in my throat. So if you wrote your answer just as this square root of y plus 1, you actually do need to start thinking in terms of all of our square roots. Whenever we take a square root of something, we get 2 answers from it. So if I do the square root of 16, I don't only have positive 4 as my answer, I also have negative 4 as an answer, because negative 4 times negative 4 does turn positive. So the way that we write this is with a plus minus sign in front, or a positive negative sign in front. It's just a plus and a minus stacked on top of each other to signify that we are going to have 2 answers. So you need to have both answers there. On number 2, first thing that we need to do is undo the fraction. So we're going to multiply by the reciprocal. So we end up with 4y equaling x squared. We're going to square root both sides to get x alone, because squares and square roots undo each other. And again, we have a positive or negative square root of 4y as our answer. On number 3, we need to first start off by taking the cubed root of both sides, because we want to undo the 3. So I end up with y equaling the inside of our cube root. So we have x plus 4. Sorry, this is inside of a cube root. That's where my brain went crazy. Then I have to do the inverse, so I have to subtract 4. So over on the left, I have the cubed root of y, positive or negative, minus 4 is going to equal x. Okay, so basically we're just rewriting things. That's kind of the vibe of the entire day, is that we just need to rewrite things. And so here we go. I don't have my stylus, so sorry about my handwriting. Hopefully you can read it all. Don't make fun of me. Pretend that you can't hear me. So the root of the matter on the next page, it says, you know that the inverse of a power function defined by the set of all points x or y, or x comma f of x, because remember y and f of x are the same thing, is the inverse, or yx. So thus, to determine the equation of the inverse of a power function, we can transpose or switch x and y again. So in the worked example, they show that if we started off with y equaling x squared, we actually switch x and y and we would get x equals y squared. Then we're just going to solve for y to get y alone. So the inverse of that function is equal to the positive or negative square root of x. So why must we write the symbol plus minus in front of the radical to write the inverse of the function f of x equals x squared? Well, to do this, we know that square roots, oh my gosh, now you're going to see how bad I am at typing. Square roots result in one positive and one negative value. This is something that we talked about on the last page. So that's why we have to have that plus minus sign. Notice that in the worked example, it does not write the inverse of the function f of x equals x squared with the notation f minus 1 of x. Explain why not. Well, it's because, let's switch up the color here. And I might have to write bigger. So the inverse of the function is actually not a function. We can only use the inverse notation when the inverse is a function. So the inverse, it's not like, it's not an actual power of -1. It's the notation of saying we're doing the inverse of f of x. So it's not a -1 exponent. It's a notation -1 exponent. On the next page, the square root function. So we can use the horizontal line test to recognize the function f of x equals x squared is not an invertible function. Horizontal line test is also known as the vertical line test. So the VLT, vertical line test, meaning that if we were to draw a vertical line straight through a graphed function, every x will only have one y. So if we use this table to do some graphing here, pause the video, graph this bad boy to start. It should be rather simple. So graph it on your own and let's see what you get. This is what I got as f of x. One thing I noticed on our test that I just graded was a lot of people were making V shapes. These are not V shapes. A parabola is a U shape. So we have to make sure that we are being intentional and making that U shape. Okay. So it tells us that the inverse of the function, oops, that's an eraser, is y equals plus or minus the square root of x. So if off to the side, we just make a little XY chart to kind of help us out and keep us organized, we want to be able to plug in and say, okay, what does this graph actually look like when it becomes the inverse? So if I plugged in 0, let's make life easy. That becomes plus or minus the square root of 0, which is equal to 0. So our first point is at 0, 0. If I plug in positive 1, I get plus or minus the square root of positive 1. So I have an answer of plus or minus positive 1. So every time I go over 1, I'm going to get a positive value and a negative value. What I want to think about as I choose my points over here is I want all of these to be perfect square roots or perfect squares, because that'll make my life so much easier. If I have to take the square root of 5, I do not know that number off the top of my head. So I'm going to choose x values that I can easily take the square root of. So my next perfect square root would be 4. And if I plug in 4, I'm actually getting plus or minus the square root of 4, which is the answer of plus or minus 2. So when I go over to 4, I have the positive and the negative value. Oops, went one too far down there. And for fun, let's do the last perfect square. So our last perfect square would be positive 9. So when I plug that in, I get plus or minus the square root of 9, which is plus or minus the square, plus or minus 3. Man, I'm just as bad as talking when I am at my house. So the inverse of f of x is now on its side. And we do have 2 points that are shared, which is pretty nice. Why would those 2 points be shared? 0, 0 and 1, 1. So think about that for a second. They're shared because they are already inverses. Right? If I switch the placement of 0, 0 and 1, 1, aren't they the exact same? Yeah. So if we have to go down to the bottom, it says describe the key characteristics of each graph. We know that the domain is talking about the x-axis. The range is talking about our y-axis. X-intercept is where our graph crosses the x-axis. Y-intercept is where our graph crosses the y-axis. So take a second and fill this out and then come back for the answers. All right, so hopefully you filled that out, and hopefully you also had a thought of, oh wow, the x-intercept and the y-intercept are the same. And what happened to our domain and our ranges? They switched, they became the opposite. So the domain of our original function is the range of our inverse, and the range of our original is the domain of our inverse. Interesting. I wonder if that's something that's going to be important as we continue on in these notes. Just something to think about. Okay, so it says the graph in question 1 shows that every possible real number has two square roots, positive and negative. When we restrict the domain of the power function, the values greater than or equal to 0. The inverse of the function is the square root function. So if I were to restrict part of my graph on the black parabola that I had here, it's basically saying, what if I only made 1/2 of the parabola show up, 1/2 of the arms show up? So if we were to connect points, all we're doing is like switching things up. So if I drew a line to connect points that are inverses of each other, my original pink point was 2, 4. And in the inverse, it became 4, 2. Equally up here at the top, it was 3, 9. And the inverse became 9, 3. All we did was switch our x and our y values like we did in the front. So if I go to the next page where I talk about restricting the domain of f of x, that's what it's asking to graph the square root of that function by restricting the domain. It's basically just saying, I want it to be all of my positive values. So I don't want any of those y values that turn negative. So if we were to do that, I still had 0, 0. And I'm looking back at my notes to get these points because I have that other page. Actually, I should just write them down. I have the space. Why not do it? So I had 0, 0. When we plugged in 1, we got positive 1 this time only. We're not looking at the negative value. When we plugged in 4, we got positive 2. And when we plugged in 9, we got positive 3. So all in all, what's pretty cool is when we have a square root function, our graph is basically one arm of a parabola. That's it, 1/2 of a U. It's like a small little, it's not even a rainbow because it's like not like rainbow shaped. I hope you guys are thinking of ways that we can describe this when we are all back together, because I want to know what you were thinking. So take a second now, think about when we restricted the domain, what changes when we narrate these or write down these things. So for our function of f of x, our domain now, our x-axis has a hard boundary at 0 and continues on to positive infinity. And our range also has a hard boundary at 0 and continues up to infinity. Our x-intercept is intercept is still 0, 0, and our y-intercept is still 0, 0. What's pretty nice is when we do our inverse, it's the exact same thing. One thing we're going to get to be really good at, especially when we get to Geometry 2 in January, is we're going to get good at these. These are quotation marks, and they mean ditto. These are ditto marks, meaning that's the same for me, ditto. We are doing the exact same thing. So the domain and the range and the x-intercept and the y-intercepts are the exact same. So does the inverse function of, or the inverse of f of x have an asymptote? We don't think of it as an asymptote because there isn't any more to the graph. We're not allowed to go anywhere else. So technically, yes, it's an asymptote, but it's not like a visual asymptote. So no, we do not have an asymptote. No, as x increases, the negative square roots, or the negative square root of x increases towards positive infinity. Man, I really wanted to spell infinity with an I on the end. That would have been embarrassing for me. And then this one says make a conjecture about the relationship. So you're going to write basically a hypothesis. What is something that you think could happen between the domain and range of a quadratic function and its inverse? So take a second, think about it. Grammarly trying to tell me things. So the domain of a quadratic is the range of its inverse. And the range of a quadratic is the domain of the inverse, or of its inverse. Yeah, yes. We're going to leave it. Grammarly, stop telling me I'm wrong. Okay, on to the next one. So we know that a square root function now has like that little half rainbow shape, but you guys are coming up with a better word. So if we're going to restrict a domain, we can look at more quadratic functions to explore that and the relationship that it'll have with the domain and the range, the function and the inverse, what's going to happen to all of those things. So if we have the function g of x equals 2x minus 4, how is g of x transformed from the basic function of just f of x equals x squared? So we know from previous lessons that when we have a number added or subtracted onto the end, that makes it go up or down. So this one's going down 4. Write the equation for the inverse of g of x and sketch its graph. So g of x is going to equal x squared minus 4, right? That's what we were given. And if we want to do the inverse, we're thinking in terms of x and y. So I'm just rewriting that with a y. And at the beginning of the lesson, we talked about if we want to make an inverse, all we're doing is switching the x and the y. So in my equation, I'm going to switch the location of x and y. So this now becomes x equaling y squared minus 4. And now we have to solve to get y alone. So to get y alone, I have to add 4 to both sides. So this turns into x plus 4 equals y squared. Y is still not alone, so we have to take the square root on both sides. So the answer is plus or minus, because we have to remember that, square root of x plus 4 equals y. If we wanted to be even fancier, we could swap out the y again for our function notation. So this would be, g inverse of x. So in this format, now we can see what's going to happen when we flip it around. So again, I'm going to make an XY chart. That's always what I do when in doubt with graphing, make an XY chart. And then we're thinking about, I have a square root, so I kind of want to make my equations have perfect square roots here. But what you'll notice is different about this equation is it's not just x, it's x plus 4. So whatever I'm plugging in for my x value, I want it to create a perfect square. So if I just plugged in 0, would that work? Yeah, because it would become, I'm going to write it up at the top, plus or minus 0 plus 4 is how much? Well, that's 4, and that is a perfect square root. So we do get the answer of plus or minus 2. So over 0, up 2, over 0, down 2. So 0 worked. If I plugged in 1, if I said 1 plus 4, does that square root of 5 make my life easy or tough? That makes my life tough. I hate it. I do not want to use the number 1. So the next perfect square root that we could do to make life easy, if I wanted to make it 0, what number would I plug in to make it 0? Well, I would plug in negative 4, because negative 4 plus 4 is 0. And the square root of 0 is 0. So negative 4, 0 becomes our new vertex point. How do I get that next perfect square of 9? Well, I would have to plug in a 5. 5 plus 4 is 9, so I would end up with plus or minus 3. So over 5 plus 3 and minus 3. So again, what happened to our u? Oh, dang it. I almost had that perfect. It flips to its side. So is the inverse a function? Is what that next question is asking. So think of the vertical line test. If we drew a vertical line through my pink graph, would it be able to make a function? Would it be able to pass? No. No. The vertical line test, VLT, is a good enough reason for me. The vertical line test. And I hate writing. I'm never going to write out vertical line test. But vertical line test is what we check or use to check if something is a function. How does the inverse of g of x transform from the basic square root of y equals plus or minus x? Well, instead, when it was our vertex was at 0, 0, we now went 4 to the what direction? 4 to the what direction? 4 left. And is that exactly what we think of when we had our functions with our quadratics? Even if we had like x plus 2, we actually went the opposite direction, because in our equation it was x plus 4, and plus 4 actually makes us go to the left. Oh my gosh, the dots are connecting. We're doing the same things that we've been doing this whole time. Isn't that crazy? So let's look at the domain and the range. So again, our domain of our normal function was all real numbers, and our range was from -4 up to infinity. For our inverse of g of x, we got the equation plus or minus the square root of x plus 4. I started writing a 4. Here we go. So the domain of this one, when we look at the x-axis, actually started at a hard boundary of -4 and went to infinity. And our range this time is all real numbers. So what conclusion can we draw about this? Well, it means that the domain of a quadratic function is the range of its inverse, and the range of a quadratic function is the domain of its inverse. So in this case, it's not a function. Our inverse was not a function. It just wasn't allowed to be one. So that was kind of the answers to F and G here. So I'm kind of getting that out of the way. We're not going to do that one. We're going to go to the bottom. We're going to go to number 2. So it says, consider the function h of x equals x minus 4 squared. So again, this is a quadratic, so it's a parabola. -4 actually means that we're going to the right. And that's exactly what happened on our blue drawn parabola. How is h of x transformed? We said 4 to the right. Write the equation for the inverse of h of x and sketch its graph. So take a second and practice actually plugging in the inverse. This is where we're going to switch x and y. So sometimes it's helpful to like write your starting equation or function. So h of x equals x minus 4 squared is what we started with. We said that we want it in terms of y. So I'm going to rewrite it as y equals x minus 4 squared. Now we have to transpose or flip the x and the y. So now we have x equals y minus 4 squared. And now we're going to solve for y to get y alone. So to get y alone, I have to square root on both sides. So I have plus or minus the square root of x equals y minus 4. To get y alone, I have to add 4 to both sides. So we're getting plus or minus the square root of x plus 4 equals y. What we can then do is graph this. So if I'm going to graph this, I have my xy chart. And again, I want to plug in numbers to make my square root easy to actually graph in my life. And yay for us, x is alone, so I could do my normal numbers of 0. So that would be 0 plus 4, which gives us 4. So over 0 up 4. If we plug in positive 1, we're getting plus or minus 1 plus 4. So we're going to have 2 answers. So 1 plus 4 is 5. And -1 plus 4 is 3. So when we go over 1, we can go up 3, and we can go up 5. If we plug in more points, again, I want it to be a nice square root. So if I plug in 4, I have plus or minus 4 plus 4. So 4 plus 4 is 8. -4 plus 4 is 0. So over 4, 8. There's a 2 in there. Sorry, I'm watching football, so like that was a bad call on my point, because the square root of 4 is 2. This is looking better. So I would have 6 or 2. So over 4, up 2 over 4 up 6. And then lastly, we could plug in a 9. So the square root of 9 is 3. So 3 plus 4 is 7. Negative 3 plus 4 is 1. So again, what do you notice happens? From the parent function, we ended up shifting our vertex up 4. So when we go to the right, we're shifting up. When we go to the left, we're shifting down. Down and left go together, just like that's where all of our negatives live on our coordinate plane. Right and up go with each other because that's where all of our positives live. So is it a function? No, it was on its side. Will not pass the vertical line test. We just said that it was going to go up. And so let's look at this next page and we're going to fill out this little chart. So it says complete the table to describe the effect of each transformation on the inverse of the quadratic function. So if we're going d units up, the inverse will go d units right. Translation of d units down will be d units left because we said up and down up and right go together, down and left go together. If we have a translation of c units, it means that we are going to go c units up because up and right. Translation left of c units is going to be c units down. That's going to be important for us to know the difference so we can kind of check ourselves. This next one I want you to do on your own. So pause the video and try number 5 on your own. It says write the equation for the inverse of each quadratic function and identify the appropriate domain restrictions. So we see here that we actually have to go -2 down, right? -2 down. So the inverse of down would mean that we're moving to the left. So in our answer, we should end up with a +2 because we should be moving left. Let's actually practice the skill though. So we would have y equals x squared minus 2. We're going to transpose x and y. So we have x equals y squared minus 2. I'm going to add 2 to both sides. So we have x plus 2 equals y squared. When we square root both sides, we end up with plus or minus the square root of x plus 2 equals y. And is that exactly what we wanted? We wanted the argument to be applied to the horizontal shift. Yes, we did it. We're amazing. So if we think about the domain and range, what should they be to each other from the original to the inverse? They should be flip-flopped. They should be the exact same numbers, but one will be written as domain, one will be the range. Okay, on part B, actually, I should actually write those numbers. So for f of x, our domain was a hard boundary at 0 to infinity, and our range was a hard boundary at -2 to infinity. For our inverse, the domain should be a hard boundary at -2 to infinity, and our range will be a hard boundary of 0 to infinity. So again, those are switched. On part B, again, we have to transpose. So if we wanted to just start with x equaling y plus 2 squared, that is allowed. You can do that. You don't have to take all those baby steps. Our first step is going to be square rooting on both sides. So we get x is equal to, or the square root of x is equal to y plus 2. We subtract 2 on both sides. So we end up with plus or minus square root of x minus 2 equals y. So hopefully you got that. And that's how far we're going to go for today. So no homework. Look at Freckle. No Freckle this week. It's a short week. Don't do that. But look at Mathia. Give it a go.